But one thing I want to point out that's different, and it's sort of a different style of problem, is static problems. It sounds like they would be easier, but they really aren't always easier. All static problems means is we did them a little bit with forces. It meant the sum of the forces in the x equals 0 and the sum of the forces in the y equals 0. So it's not moving. Now we're just going to add that the sum of the torques equals 0. It's also not rotating, right? If it's not moving, it's not rotating. But we have a special superpower for rotational static problems, and that is we can put the axis anywhere we want. Right? So if you say it's static about this axis, well, it's also static about this axis, and it's static about that axis. So you can build up all the formulas you want by saying this is true. A lot of them might be not giving you new information, but the way you pick them can actually help you out quite a bit. Oh, plenty of time. So let's do the famous ladder problem. Oh, yes. Here we go. So you got a ladder at like 60 degrees, like that. Here's a ladder. It's against the wall here. Right. Ladder. This wall is, this is an ice wall. This is frictionless. Ooh. So this is a frictionless wall here. So there's no friction force on the ladder here. This has a static friction mu s down here. So if you think about it, if they were both frictionless, the ladder would fall. Right? We don't want to do that. But if only one of them is frictionless, if only the top is frictionless, that just makes the problem easier. And the question in this problem is, what mu s to keep the ladder from falling? And we don't really have time to do it in perfect, clear detail, so I'll video it, but let's just get it started. Let's get the important concepts going. Okay. First important concept would be to label all the forces. We don't do as many free body diagrams now because we're thinking about the size of an object. But the forces, there's always that one. Okay? If you're in the exam and you have no idea what to do on a problem, there's 30 seconds left, you didn't do a whole free response, just draw whatever shape and put like mg with an arrow down in the middle of it. Okay? You'll get a point, right? You'll get a point. So mg down this way. The normal force this way, I'll call that N2. And the normal force is going to be up that way. We'll call that N1. And then there can be friction here. And remember, static friction fights the pent-up desire for motion. Which way does this thing want to go? If this were frictionless, it'd go that way. So static friction is that way, Fs. Right? So we have 4 forces to deal with. Normally, there'd be a static friction up here because the pent-up desire to move is down, but we said this is frictionless to make the problem, doable. Okay? So that's the question. So what we would do then is to start to say, just start to write the sum of the forces in the x, sum of the forces in the y, and the sum of the torques, right? So in the x, all we have is N2, we're going to do magnitudes, minus Fs equals what? 0. This is a static problem. This is the good part about static problems. 0. There's the x. Right? That's the x direction. Let's do the y. Oh, it's not so bad. N1 up minus mg down. It's not moving in the y. Okay? And now, here's the big one, and I'll just tell you. Now you got to pick where you're going to do the torque. You got to pick your axis for the torque. And I'm not going to tell you. I'm going to make a video of it so y'all can think about it. Or if I get busy, I'll do it Tuesday. So which axis would be the wisest choice? Mystery for the ages.